Hello and welcome to today's MCES Social Science Data Lab. We're very happy that Leah von der Heyde is here today and will present about Ain't Nothing But a Survey using large language models for coding open-ended survey responses. The Social Science Data Lab is an event series here at the Mannheim Center for European Social Research, where scholars present tools and methods for the collection, analysis, and visualization of data in the social sciences. Our speaker today, Leah, is a computational social scientist and survey methodologist at GESIS, Leibniz Institute for the Social Sciences, where she's part of CODAX, the Competence Center for Data Quality in the Social Sciences. She received her PhD in social data science and research methods from the University of Mannheim and has a background in political science from LMU Munich, University of Mannheim, and Georgetown University. Before joining GESIS, she was part of the Social Data Science and AI Lab at LMU Munich. In her research, she focuses on the potentials and pitfalls of new data sources, such as large language models, for improving the measurement and representation of public opinion. Substantively, she's particularly interested in political attitudes and voting behavior. In this talk, Leah will demonstrate how large language models can be used for classifying open-ended responses by using different access options, prompting, and fine-tuning techniques. She will present a study that tests these approaches on a dataset of German open-ended survey responses, and we'll discuss what these findings imply for practitioners. Just some note on housekeeping. Please know that we're recording this live stream in active speaker mode. So the audio from on-site and remote participants will be recorded. And for those of you joining online, if your video is turned on while asking a question, your video will be recorded as well. Leah, thanks for being here today.
Yeah, thank you so much, Alex, for the introduction, and to the MCES for having me. You already mentioned the title of the talk, so I don't need to repeat it. We're going to be talking about the use of LLMs, coding open survey responses. What I aim to cover with you guys today is starting off with just some general approaches and challenges that we have when coding open-ended survey responses with and without LLMs in general. We're going to do a little recap of how LLMs work and how we can work with them, just to get everybody on the same page, because I understand that, not everybody is using them every day and in different forms, so that we then actually know and understand how this was actually implemented. I'll then walk through the research design of the study that I want to present, show you how I implemented this. So there's going to be some screenshots of code, just to kind of it's not going to be hands-on, but to give you an actual idea of how this can look like in practice. And then I'll show you the results, and we'll have some takeaway learnings from that. And then I'm happy to discuss anything with you. I aim to not talk for more than 60 minutes, so that we have enough time for discussion at the end. And also because I think attention spans are exhausted after 60 minutes already. So we'll see how that goes, because I haven't test run this, but we'll see. So let's start. Traditionally, when we're coding open-ended responses, we had humans do this, right? The pro of that would be that they're ideally very accurate. We can train them, we can instruct them if it's like a student assistant or something. And they're also quite reliable, simply because we hope they're consistent in their training. Of course, unfortunately, it's a rather cumbersome process, which means it's not very fast. And also, human labor is expensive if we're paying fair wages. So pros and cons of traditional, human-coded approaches. Then, of course, there are computational approaches, so more traditional machine learning approaches. So this could be, for example, support vector machines, gradient boosting, random forests, but also analytical LLMs. So before we had GPT and all of that, that was BERT, and BERT was used a lot for classifying all kinds of stuff, including open-ended responses, which is nice because it's much faster than having it being done by a human. However, there's a lot of cons to it, because you need some expertise for actually setting up these models and running them. You need the computing power to run them. You need to pre-process the data, because open-ended responses come in all shapes and formats, and in order to be able to classify them, you need to clean them up a bit. You still need some human-coded training data to train the models. And then a lot of times, especially with open-ended responses and surveys, they're really short and they're lacking context. And that's something that these older machine learning-based approaches don't really work with very well. So it's not a very generalizable approach, and still needs a lot of work before you can actually use it. Now enter large language models. which are promising to be rather flexible across languages, across different types of text. They can process all kinds of stuff. They're also really good with texts that don't have a lot of context, so that's precisely what open-ended responses always are. You don't necessarily need to fine-tune them. You can just throw something at ChatGPT and ask it to do it, and it can do it for you. And they're really accessible because, again, I think most of you at this point have interacted with a large language model in the form of a chatbot in some way. We don't really know a lot about the cons at this point, and this is what we want to talk about a bit today. The point is that the evidence so far, and when I first conducted the study, this was 1.5 years ago, so of course there has been some progress since, but still the evidence that there is really scarce, and it's competing. So there's very few studies that actually use open-ended survey data. There's lots of studies using LLMs on all kinds of different text data, but just not specifically open-ended survey data. And the ones that do really look at best case scenarios. So we have this study, for example, by Jonathan Mellon and colleagues that is looking at the most important problem question, which is really common in societal surveys, and they're looking at the British one. And so there, of course, the most important political problem, that's a really straightforward thing that's probably also discussed a lot and also in the English language. So that's kind of like a best case scenario for LLMs for classifying these reasons that people give or these problems that people give. And so the gap really is looking at this for harder cases. So for example, for survey data that isn't English, for topics that are less common, for different prompting approaches, and not just comparing a single one in a single study and then the next study uses a different data set with a different prompting approach. And once again, also comparing different LLM families within the same study and all of these factors combined. So we can learn a bit more about the generalizability of these findings. So these were actually really positive, depending on the LLM or whatever, this worked quite well, but we don't know whether this applies to other contexts. So the research questions that I wanted to answer with this project were really whether there's differences in performance and reliability of LLM-based coding, depending on what LLM you use, depending on what prompting approach you use, looking at a few different ones. So depending on whether you use descriptions or few-shot prompting or fine-tuning, for example. And to those of you for whom these kind of terms might be unfamiliar at this point, this is exactly why we're going to do a quick recap on how LLMs really work and kind of focusing on what's relevant for the study that we're talking about here. So really quick, of course, what are LLMs? When we say artificial intelligence, that's actually, can we see that? It's very low contrast. Yeah. We say artificial intelligence, but what we really mean is down here, right? So artificial intelligence is a really big pool. There's machine learning. So of course, large language models are a part of all of these bigger buckets, but we're really focusing only on this part down here. So what makes them so special is that they're generative, which means they both process and produce natural language. You get a natural language output, and they learn patterns in the language based on their training data, where they create associations between embeddings in a multidimensional space. What does that mean? So the training data is this large corpus of internet data that is generated by humans, and from that, the LLM kind of understands how human language works and what are associations between words. And it does that based on embedding. So those are kind of numerical representations of words. And then you can think of this as correlation. So man is to woman as queen is to king. And so the embedding space between those words would be kind of similar. And that's how an LLM learns to make these predictions. And they're usually multi-purpose and multilingual. They usually work better for English than for other language, but in general, you can use them for a large variety of things. Now, I already mentioned the keyword probability, right? So an LLM is probabilistic, which means it predicts the most likely next word in a sequence, so in a sentence, for example, conditional on the prompt. So whatever you put in, it then predicts iteratively what should come out. So for example, here you have the sentence, where are we? Here we are. Hooray, I'm spending my summer at the, there's going to be a probability distribution. And the probability for the sentence we completed with the word beach is a bit higher than for this to be completed with the word MZES, which still maybe is better than prison. So we're happier to be at the MZES than at prison, but the beach would still be better. The point of this exercise is that if we change the prompt, so for example, if we put "oh no" here, then the probability for prison will get much higher. The probability for MZES will probably get much lower too. So it's unlikely that we're unhappy about spending our summer at MZES. So we see that this is a conditional probability, and this is autoregressive. So with every new sentence or every new word that we put in the prompt, this probability distribution also changes underneath. Now, I put a little asterisk here with the word prompt, if you have noticed before. That's because technically this is not about words, it's about tokens, which is the smallest unit that a word can be decomposed to. And so, for example, OpenAI offers this tokenizer where you can put in a sentence and then it transforms it into tokens to you. And you see that tokens don't necessarily correspond to characters or words. So we have the word hooray, which is like decomposed into 1, 2, 3 tokens, and then the comma is its own token. Spending is its own token of itself. And this is important to remember because tokens are associated with cost if you're using more advanced models or something that goes beyond the free version. Now, there's different ways of interacting with an LLM. You can conceptualize them or kind of like different ways of drawing, like drawing onto the knowledge of LLMs. And conceptualize 3 broad categories, which is, again, where are we? Where? Retrieval augmented generation, prompt engineering, and fine-tuning. These 2 are probably the ones you've heard about more, and these are also the 2 that we're going to be talking about today. We're not going to be talking about RAG. So let's look at a few different prompting approaches. There's zero-shot prompting, which basically means we're instructing a large language model without any examples. So for example, classify the reading level of the following question, and the question would be, do you love this talk so far? And then, the LLM would say the reading level of this question is 5th grade. Now, in few-shot prompting, what we're doing is we're providing examples of the desired output in the prompt to the LLM. So we say, classify the reading level of the following question. What we give examples. So for example, do you like going to these SSDL talks? The reading level would be 8th grade. If you think this presentation is fun, the reading level would be 4th grade. And based on these examples, what's the reading level of, do you love this talk so far? And then it would maybe say reading level 5th grade. And you see here, it's already learned kind of like the format that we want as the output here, right? Like the reading level, call it 8th grade, and then it does like reading level 5th grade, ideally without us having said that, where before it maybe put out an entire sentence. Now, fine-tuning is kind of doing a similar thing on the back end. So where before we're actually interacting with the model, we're readjusting the internal prediction weights. So how the LLM generates a probability distribution for a specific application, because we're giving it, again, input-output pairs as an example, but on the back end. So we're like doing this before we even asking it to do anything. So we give it a little data set of a few input and output examples. These might be the same as we showed before. And we put them in, and then we prompt the model. And once again, we ask it to classify. And then it might actually give us a more precise categorization because we gave it more examples and because this was based on the internal adjustments. There are a few other things that we can influence when we're interacting with LLMs, so-called hyperparameters. I highlighted the ones that are relevant for us today. So the most important one would be the temperature, which talks about how much weight is given to less likely completions. So if we're, again, thinking of this probability distribution, this is really about modifying the shape of that distribution. And if we have a higher temperature, we have more of a uniform shape, so less likely completions will be weighted up and will be more likely. And if we have a lower temperature, then we're going to be tending towards the most likely completion there. Another important factor is the maximum tokens, with which we can determine the output length. So if we don't want the LLM to ramble on forever, we can say, hey, only put out like 600 tokens maximum or something, or even 50 or 30 if you want like only a sentence, which can help make the LLM kind of like really concise, but it could also just mean that it cuts off whatever it was about to say. If it had a whole monologue prepared and you limit it to like 30 tokens, then you might just have an incomplete word and the rest of the sentence is just not there. And then another important aspect are the seeds. which are fixed starting points for a random draw. So some of you might know this if you're like working with R, or like any of you have taken like an quantitative methods course in grad school. Then you're also like, seeds from kind of like, making your workflow reproducible. And this is something you can do with LLMs as well. So that ideally, it's not 100% sure, but that you can recreate the same kind of sampling process and get the same completions, which is important if you're doing research and you're publishing a paper and you want other people to rerun your analysis to see. So that's helpful. We can distinguish LLMs by whether they're open or closed. So this relates mainly to transparency, privacy, and accessibility / cost. So there's open source models. There can either be open source with fully open like source code, or just open weight, where they just tell you about the weights, but not really what training data they used. They're usually free. So for example, this would be something like Llama from Meta, or Mistral, which is a European LLM. You also have stuff like Quen or Gemma, or very new Kimi. Those are all open source. And then for open weight, for example, you now also have DeepSeek, but also the OSS suite by GPT, which is also open weight only. And then, of course, you have proprietary models such as like your Claude, your GPT, all of that. And then another aspect is how big models are. So you have large models, you have medium-sized large language models, and you have small ones. And so, for example, a large one would be like GPT-4, a medium one would be like Llama, and a small one would, for example, BERT, which again is more an analytical thing, and we don't care about so much about that. Different ways of interacting with LLMs pertain to, this is something probably you know, this is the web interface. You open chatgpt.com and you just type in your little prompt, and then you get a response. Which is really nice, but also there's a limit at some point you run out of like free use, and you probably have to sign up for a subscription. Something more advanced is the playground or sandbox, where you actually can customize the hyperparameters that I just talked about, or you can even use them for fine-tuning, which you can see here. And there you definitely still need a subscription to do that for proprietary models. But it's a really like nice user interface for actually playing around with these hyperparameters, kind of in a just very user-friendly way, because you just drag a few sliders, if you will. It's kind of like the SPSS of interacting with LLMs. And we know how we feel about SPSS, maybe. We can also access them via APIs if we want to go more into like an R direction, if we're sticking with the analogy. So here, this is an example from a different paper of mine, where I use the RGPT package, which basically accesses the GPT models. And there you can set seeds and put your max tokens and your temperature and your other hyperparameters, like just directly in the code, and then run through your data set and do that. But of course, if you're using local open source models, you need to host them locally. So you can get them from platforms such as Hugging Face. And then if you don't have your own computing resources, you can, of course, access them through something like Azure, which is Microsoft's cloud computing. But there, of course, again, you need to pay for that. So it's not really free. The model's free, but you need computing resources, and you might have to pay for those. And then there's new stuff like LM Studio, which kind of like tries to bridge that you can actually run them locally, privately on your own resources, but still somehow have the compute. So that's a new option. Quick ad break. I hope you're all now on the same page as I am when it comes to like how LLMs work and how I want to set up the study. So recap, we cared about kind of like how different LLMs and prompting approaches impact the performance and reliability of coding open-ended responses. And so the use case I'm going to be presenting today for this study is German open-ends on survey motivation. So reasons why people participate in a survey. And this is what the title of the talk comes from, because I hope you're leaving this presentation with a little earworm. So if a survey researcher asks, tell me why, are you participating in the survey? And people just say, well, it ain't nothing but a survey, I just participate. So this data comes from the Guesses panel. We sampled a data set of a little over 5,000 open responses. you have, for German speakers, the original question here on top and the translation at the bottom. So it's really about for what reasons do you participate in this survey? And then please name your 3 most important reasons. And you have 1 line for each reason, which is a nice setup because it usually leads to people really just putting in 1 word per line, and there's not a lot of cleanup necessary. You have like 3 reasons maximum, and then we aggregate those. The coding scheme that was developed for this has 22 categories. It's a multi-class single label classification. What does this mean? That we have several categories, so 22, but we only ever assign 1 label to each response because they're so nicely unidimensional, which is nice for the LLM. What's hard is that this is a very specific topic, survey motivation. There's not a lot of info out there on that. And also, it's a lot of categories. It's a very complex. It's not just yes, no, binary, positive, negative. It's 22 possibilities. And of course, it's German, so that's a bit of a harder case. And we actually, in a previous study, there was hand coding done for the entire data set that we have here. So 2 people coded this. So we have a verified benchmark that we used. So how did we do this in detail? So like I just said, we have this coding scheme, we have the raw data, and we prompt the LLM with that once in a 0-shot setting. So what I just said, no examples, nothing. We just say, hey, classify this open-ended response. Then we also experimented with giving it definitions of the categories that were also in our coding scheme. So kind of like also what the coders had as a reference for what it should belong to. And then we also did few-shot prompting. So we gave actual examples. Remember, then you have the task and like, here's an example for this category. And we could give those because we had the human labels, right? So we actually had verified examples. Those same human labels also helped us to fine-tune a model. So there we split the data into a training data set where we readjusted the internal weights, like I just said before. And then we tested it on the remaining data so that it hadn't seen the same data before. The LLMs that we used in this study were 2 open source LLMs, so Llama and Mistral, and the proprietary GPT. For model versions, keep in mind that the study was done in the fall of 2024. So of course, this is not going to be the newest versions of GPT, but back then it was. And from that, we got the labels. So we kind of, like you see here on the left-hand side, kind of have 2 variations of, like 2 dimensions of experimental variation. So the content were varying and the LLM were varying. And then, of course, our human labels are the benchmark for what we get out of the LLM. So we compare to that. How is that implemented? Here you can see the prompt that we gave to the LLM. We did this in German, but for illustration purposes, this is English. And notice what I did here. I told it it's a survey expert, right? So I was already like putting it into the mindset or hoping to draw its like condition the underlying probability that it's being like to kind of like draw on what survey researchers would associate with this task. I was also very clear and specific. I said assign these reasons for participating to exactly one of the following categories so that it would do this multi-class single label thing and not just give me a bunch of labels. I also said make your best guess. And I gave it the format that I wanted so that it would be easier for me to actually process the output so that I wouldn't have to go look for the response and the reason, and to make sure that it actually classified the correct response so that it didn't give me something else and classify that. And I also tried to stop it from rambling because I didn't want to pay for too much. So I said, don't give an explanation. We don't want like chain of thought prompting here or anything. Like just give me the label at this point. And then here you see for experimenting with the descriptions, we put not just the categories, but we also gave descriptions of each category. And then, I guess I forgot a little circle here, but then for the few shot version, we had examples that we put, and keep in mind that we always randomize these categories so that it wouldn't just always pick the first category or something.
But they have names, not just numbers, right?
Yes, of course. So
yeah,
this is just a template. Yeah,
no,
it's fair question.
Sure.
Absolutely. This would not be helpful. Now, I told you about hyperparameters. These were the ones that we used. So I set the temperature to 0. Remember, lower temperature means getting the more likely label. And in this case, that's what we wanted. We didn't want the LLM to be creative. We just wanted the most likely category that this belonged to. For most models, or like for GPT, we didn't set a limit, but from a previous study, we knew that especially Mistral was prone to rambling. So we said, okay, please do not talk for more than 600 tokens. And that actually worked quite well. So we didn't get any cutoffs or anything. That was good. We only drew one sample, but we did through 2 independent runs through each data set so that we could compare if the reliability was there. We reset the prompt or like the model after every prompt so that it wouldn't learn from its previous assignments, so that every classification was made independently. All other parameters were left at default. And like I said, it was a data set of about 5,000, but for the fine tuning, it was only 1,000 because we used 4,000 something for training the model. Now, this is where the promised code snippets come in. For GPT, we accessed the model via Azure OpenAI because open-ended responses are sensitive and we don't want to give them to any third-party servers. So at least something that's hosted within the EU is covered by GDPR. If we can't host locally, and of course, GPT is always it's proprietary, so it will always go to their servers. But through Azure, there are at least European servers. So we did that. You need a license for Azure, so kind of like a subscription for GPT, but a bit more complex. And there's an R package. It's called Azure Auth, and with that, you can access it. I put a little smiling tear emoji here because, as you can see, the setup here was a bit of a pain. It required quite some Googling to actually just log in. So the blue circles are the logging in part where you have to put in your different login tokens. And then the pink part here is where I actually access the model. So that was easy, but the other part was a bit of a pain. And you can compare that to Llama and Mistral, which we downloaded from Hugging Face and then implemented in Python. We had a server through the university with an A100 GPU, so we didn't have to buy any compute. We just had it, which was nice. Loaded a few packages, and this was super easy. Just put in like a Hugging Face login ID, 1 line of code, and then I accessed the model. So I never thought I'd say this, but in this case, Python was actually easier than R. Now, once again, for GPT, actually running the whole thing was defining. So here you have to look on the right-hand side first, defining kind of like the roles, user and content, and then looping through the entire data set row by row, because we were resetting this after every open-ended response. And then it was here calling the OpenAI API, the client and deployment name. And then here, this was actually a function that we wrote, and this is what's here on the left-hand side, where we were setting the seed and the temperature here in pink. And then here, transforming the data into the format that it needed, which is a JSON format, so that we were actually transforming our raw text prompts into a format that the LLM could actually work with on the back end and then loop through that. Luckily, also there's a package for that, so you don't need to do that manually. And then in parallel, in Python, what it looked like is that we looped through this entire thing. So there was a little loop function, and then also here you could determine the maximum number of tokens. Like I said, here we put 600 because we didn't want it to ramble, set the temperature to 0, and then it just looped the entire thing. I mentioned JSON, and this is something that we're going to look into a bit more. So especially for fine-tuning, this is something that you need. At the top here, what you see is kind of like the raw data set. So we have a little ID, we have what people put in as a reason for participating. So here it says basically important for society, important insights, telling my opinion, fun. People think surveys are fun, that's great. And then here we have the code that the human coders assigned to this. And then here we have the prompt. It always starts the same. It says like, you're a survey expert. But then, these reasons are pasted in there. So if we're zooming into this, this is what it looks like. You're a survey expert, like I showed you before, and then it puts the categories here in a new line every time. That's why there's these /n line breaks.
and then it puts the actual open-ended response that is supposed to be classified. Okay, that's the prompt that we're getting. Now, in order to be able to work with fine-tuning, we have to use a different format. So what we do is that we split it into a training and a test sample, and for the training data, we paste this prompt that we had, and then we paste the desired human code as a completion. So we say, if this is what you're getting in, which is the prompt with this little reason that you're supposed to classify, then this is what you're supposed to be putting out. And we do that for 80% of the data so that it gets like 80% examples to readjust its weights. And then when it gets the 81% for testing, then it then knows, well, now I've learned this. So now I'm going to be completing it with something that I learned from these. So basically, if I say A, you say B, and it's learned from that. And that's something that you can do easily in R. Once again, there's a package for that. And then it just transforms that into JSON. And then that's what it looks like. So you have a little JSON file that you can then fine-tune your LLM with. It looks really similar. It just has a different format when it comes to like squiggly brackets and then kind of roles. And here you say, this is what the user puts in, and then this is what the LLM is supposed to be putting out. That's the role assistant. Last thing you need to know for understanding what we did, if you're not from an NLP background, is evaluation metrics. So traditionally, we use something like intercoder reliability, or like maybe kappas or something if we're working with human coders. What's often used in NLP is stuff like accuracy or F1 scores. So accuracy is basically just the share of correct classifications out of all classifications. This is problematic for imbalanced data. You may or may not recall from before where we saw the distribution of the human data. This is imbalanced data. So the problem here is that, for example, if you have 95 positives and those all are classified correctly, but you have 5 negatives and they're all classified wrong, then you have 95% accuracy, but the 5% of cases that you care about, they're not classified correctly. So that accuracy doesn't really buy you anything. Then we have precision and recall, which are kind of like similar concepts, but relating to like different denominators. So we're looking at the correctly classified positives, once related to everything classified as positive and once related to everything that's actually positive. And then if we try to like combine those together, because those are both informative, we look at the harmonic mean, which is an F1 score of precision and recall. And then what we used in this study was the macro F1 score, which is the unweighted mean of the per class F1. So remember, we had 22 categories. And for each category, we calculate this F1 score. And because we think categories that don't occur a lot are just as important as the ones that do, because all reasons for participating in a survey are equally valid. So we want to, classify them the same. We give them an equal weight. So even the smaller classes have an equal weight. So macro F1 is what we're using. Finally, get to some results. So we asked, tell me why. The survey participants said, ain't nothing but a survey. What did the LLM say? Ain't nothing but a mistake. So they weren't very good at classifying this. What I forgot to mention, macro F1 ranges from 0 to 1. 1 is better, 0 is the worst. We see that the performance really depends on the LLM that we use. So GPT, 0.67, that's pretty okay. But if we're looking at the open source models like 0.34, 0.4, not so great, especially if we're looking at zero-shot prompting here. Now, this is a matrix, and if we're looking at the rows here, we see it also really depends on the prompt that we used. So for zero-shot prompting, this is much worse. For example, in Mistral here we have 0.4, but then if we're using few-shot prompting, it's better. We're at 0.58. Not so much of a difference for GPT, so we have an interaction here between the large language model and the prompt. Lastly, it also depends on the category. So remember, this macro F1 is kind of the average of all of these individual categories. And we see here, incentive was actually the most common category. So why do people participate in the survey? Because they get money for its prize. Surprise. Really good performance. All models kind of like score above 0.8, no matter the prompting approach, GPT even 0.91. But then we have this like non-substantive category, which is non-identifiable other, like they just said math or no reason, which is kind of just below here. Really, really bad performance. And so of course that impacts the overall score. But we see all models kind of like perform similarly badly here as well. There's kind of like these middle ground categories, health science, where that are also kind of middle ground in terms of performance, but here we again see GPT is much better, which then that's what it counts for, GPT also being much better overall. But if you may have noticed, where's the fine-tuning? Actually, that was a spoiler. We're not entirely done yet here before we get to the fine-tuning. So this differential performance actually affects the distributions. So here in purple, we have the human distributions, and then we have the different models. And you see there's some spikes out here. Some categories are more present if we're using an LLM as a classifier than if we were using a human, especially with Mistral, actually. And also, it led to there being a lot of NAs. So, of course, no NAs in the human coding. We coded every single response. For some of the responses, when we use GPT or any other, like the other LLMs, it just said, like, I can't classify this, or just didn't return anything. There was actually missing values. That's not something you want. So, this is why we're saying, I never want to hear you say NA. Now, I want it that way. So people are laughing. If we're fine tuning, and we only fine tune GPT because we couldn't fine tune all of our models, much better. Jump in performance, even for this model that was best performing. We now have a net one score of 0.87. Compare this to a more traditional approach, which is a support vector machine that had 0.83. So here we're actually nearing something that we could have achieved with an older approach. Finally, took a lot of work. And then we also see this, don't be scared, I know this is a lot of data. We also see the performance. So you see here the little peak now, the non-identifiable other category, which I showed you before, which had like terrible performance, now all of a sudden has 0.71. So the fine-tuning here really did something because we gave it a bunch of examples for this category that was meaningless and that was really hard to classify. And you see the same thing here with other survey characteristics. Terrible before, and then all of a sudden it works really well. Brevity, score of 1, perfect score. Anonymity, always had a score of 1. That was just really easy to classify. So you see here very differential performance across categories, but fine-tuning helps all of them and makes every single one better, except Recruiter that made it a bit worse. That's interesting. Okay. But that's what we want. And a wonder, that also means that the distribution is almost perfectly aligned with the human distribution. Almost no NAs here anymore. That's good news. I also mentioned that we ran each of these models twice. So we reran the entire data set through each model twice, just to kind of compare whether it would put the same classifications if we ran it a second time shortly after each other, so with a few days delay. And it's really high reliability, but it's not perfect, even though we set the temperature to 0. Mathematically, you can't set it perfectly to 0, but that would be getting too far into the matter. What it means is that we never fully get the exact same completions. We should, but we don't. So LLMs are probabilistic, and at some level, we don't have control over what they will show. This is, by the way, ICC, so two-way agreement between two rounds of coding. What did we learn from this? I am talking much faster than I thought. I hope you're all following. If not, please ask questions. First learning. GPT-4o, which was much better than the Mistral, Nemo, and the Llama 3.2 model. We also saw that there was this high short-term reliability, but we don't know how this actually reproduces in the long term, especially for proprietary models, which kind of leads us to this whole thinking of trade-offs between using open or local LLMs versus proprietary ones. Because of course, the open ones, they're free, you don't need to pay for them, you can just download them from Hugging Face after logging in. They offer privacy because you can run them locally, no requirement for running them on or sending your data onto third-party servers like GPT, and then it lands in the US, and we don't know what happens with it. It's also better for reproducibility because, again, you have it locally. Nothing can change. It's the same once you download it locally, you just have it. So that's good for science. However, you, once again, need computing resources, so kind of like same as before. Also, we saw that the performance was worse than with the proprietary model, right? And now there's actually only in the recent days, there were newer open source models that came out, that's why I put a little asterisk, that outperform really like known and big proprietary models on common benchmarks. However, you can put an asterisk to the asterisk because those benchmarks are usually not what we care about in survey research at all. These are like kind of, I don't know, how well does an LLM score on a math test? Is it smarter than a fifth grader? Is it smarter than a college student? How good is it at solving, these, or like even like coding, like computer coding tasks? It definitely wasn't scored on how well it performs in coding open-ended responses. So just because something performs well on like general LLM benchmarks doesn't mean it's necessarily so good for the specific survey research task that you want to use it for. Same with expertise. Like I showed you with the code, like it's a bit of a pain. You have to have at least some coding and LLM expertise to be able to set this up with an open source model. It has gotten easier over the past 1.5 years since I did this. I probably wouldn't do this the same way. Again, can't tell you because I have yet to rerun this if I wanted to see. But it has gotten much easier, but still you need some sort of propensity to kind of like be getting into setting up these models and understanding how they work. Now, proprietary models, on the other hand, we see they had better performance, at least in the study. You don't need any own computing resources. Those are the pros. However, they cost money per token. Depending on how complex your task is, this will get expensive quite quickly. I can talk a bit more about cost. Like I can tell you what the total cost was for this. It is, of course, still much less than if you were asking a student assistant to code this for you, because hourly pay for a student assistant is higher than, yes. So, but it is more expensive than an open source model. So depending on what you compare to, privacy, huge concern, and reproducibility, exactly for the trade-off that I just mentioned before. So it's just the opposite. Second thing we learned, few-shot prompting was better than zero-shot prompting, but only fine-tuning was satisfactory, which is, if you think about it, rather inefficient. So if we're thinking back to where we started, we had these kind of like ML-assisted older approaches that we thought were much faster. And then we thought, okay, well, large language models, they're more flexible, low context capacities, which are good. We don't need pre-processing. And we had hoped, well, they don't necessarily need fine-tuning as opposed to BERT or anything else. And they're nicely accessible via ChatGPT, and we can just type that. Well, we can scratch that. If we want good performance, then we still need to do fine-tuning. And that's not as easily accessible as just typing it into your ChatGPT window. We don't need pre-processing. That's why that's grayed out. And the context thing still isn't a problem, but we do need programming expertise. We need computing power, and we still need human coding training data. So that combined with kind of like the cost factor from before, you still need to pay somebody to do that for you or do it yourself, at least to some degree, if you really want good data, because if you want fine-tuning, you need human-coded training data. Difficulties with non-substantive categories, as we've seen, super bad performance if we don't fine-tune. Those are really common in open ends. Have you ever gotten a survey and at the end you have a little open-ended question? Anything else you want to tell us? Well, you put a dot if it's mandatory. Otherwise, you just put nothing, or you put like no reason. This is really common. So if an LLM has issues with that, then that's actually not super helpful in the context of open-ended survey responses, unless, again, we fine-tune. And we've also seen that there's distributional differences. So one thing I haven't done in this study is that I've looked at kind of like correlational factors of like that in relation to what these responses were classified to. Other studies that have come forward since then have done that and have actually shown, for example, that LLMs perform differentially well depending on who writes the text, not because they know who writes the text, but writing styles, for example. And writing styles can be associated with, let's say, gender, ethnicity, language proficiency, something like migration background, all of these things. So depending on that, if an LLM performs differentially well and leads to different distributions, and also even just more simpler substantively, if we're trying to understand what motivates people to take a survey, and it wasn't, an LLM doesn't classify incentive as the majority category, but I don't know, something else like fun, then what does that mean for how we incentivize people? What incentives do we offer? But also then, what do we learn about the different subgroups? So how we classify and what we classify really makes a difference for the learnings that we have, that can be really dangerous if we really want to get it right. And then, of course, we've also seen that the performance of the prompting approach really is conditional on the LLM that was used. We've seen that in the little matrix, right? For GPT, it didn't make so much of a difference unless we used fine-tuning, and for the open models, it really made a difference whether we put examples or not, which generally then leads me to say that there is no one-size-fits-all approach. It really depends. What prompt do you use, and with what LLM do you use what prompt? I can't tell you, you should use this prompt and this model, because it really depends, and these choices also depend on your individual setup. Still many, many open questions. That's why the text here is slightly smaller, because I tried to fit them all on one slide. And on the one hand, there's all of these data-related open questions. So this was a very niche topic, but of course one should more systematically compare common topics versus niche topics within the same research design. So something like most important problem would be a very common topic. We have niche topics like survey motivation, so many other topics in between. Like I just mentioned, performance for different writing styles is not something we actively investigated here, but that can definitely have an impact, and then biases towards different subgroups and how well we understand them. Also, how do LLMs perform for different question formats? So here, like I said, we had this really, let's say, it was a really nice format for coding open-ended responses, because it was just these single keywords that people put in the survey based on how the question was formatted. But of course, there can be more complex questions. People put entire paragraphs that will be harder to classify. And also another thing, of course, is whether you assign one label or several, right? There could be, especially in a longer text, several themes that pop up, and you want to ask the LLM to classify all of those, and then that might actually be much harder. I think there's a paper that actually found that performed better. But again, single paper, we don't really know the big picture there. And once again, if we're looking at downstream analysis, how does this actually impact multivariate analysis based on the data that we had classified? When it comes to LLMs, so many more questions. So like I just mentioned, this study was done 1.5 years ago, and of course, newer models have come out since then. So this is a moving target. Like anything I tell you, and this is being recorded, it's going to have a short shelf life. We can only, at this point, identify general trends in time and kind of how things were and how much progress we have made ever since we did that study. So at least we have some sort of benchline. When it comes to fine-tuning, how can we further improve open LLMs, or have they improved since? Also, what's the minimum amount of training data that we need? Like here we had an 80-20 train and test split, simply because that's quite common, but also it was quite a small data set compared to other fine-tuning exercises. So this was 5,000 responses in total, and we had 4,000 for training, 1,000 for testing. Still, asking somebody to hand code 4,000 responses, it's not that little, right? So can we optimize this? What's the minimum amount that we still need to pay a human for before we can give this to a machine? And also, what are alternatives? So, for example, we could try and remove unusable answers first. So all of those non-substantive like X, stop, meh answers, we don't really learn anything from them anyway. So maybe we could throw those out in the first step, and then performance on the other ones would be much better, and that would already save us quite some time and resources. We could also try and prompt tune. So for example, by giving even more explicit instructions, by explaining that it's really important to always assign a category so that we could, for example, avoid those missing values that I showed you. Another thing that we could do is prompt chaining, which is kind of like breaking down the task into a two-step process. So for each category in this case, we could say, hey, can you tell me whether it belongs to this specific category, yes or no? And then for the second category, yes or no. So we're binarizing this task, which then again might make it easier for the LLM. We don't know to test it. But that would kind of like reduce the complexity because the prompt wouldn't be that long. It would only ever have one category, and then the next prompt, a bit inefficient though, if you think about it as a workflow. And then of course, another option would be RAG, which is the one application that we didn't talk about today, but actually drawing onto like a data set in the background where it has some sort of ground truth to try and have that as an alternative method. Another big question is uncertainty estimation. We can traditionally form like confidence intervals around LLM estimates because the data generating process isn't the same that we have when we're looking at human generated data or sample data, but also on a more applied level of uncertainty, like how, since this is a probability distribution, how sure are you actually that this is the label that this response belongs to? We could ask the LLM, how sure is it? And it just gives us a certainty based on its internal distributions. We could also do several iterations and then see whether it's consistent and see which label comes up the most. If we're doing 3 iterations, we do a majority vote. If this category pops up 2 times, this category 1 time, we take the one that's classified as 2 times. Or we could try and look at the token probabilities. So we get the probability for the output, but we also get the probabilities for the next most likely output, because actually sometimes there's a mismatch. Sometimes what we see, what an LLM gives us, a text output, isn't the one with the highest probability, because it samples from a distribution. We can influence that distribution, and we can try and steer it towards the most likely token or word. It doesn't always do it. So that's another way of saying, kind of like, how sure are you? How likely is this? Is it more likely or less likely than another? Finally, if we're thinking of humans that are labeling data, of course, they come with their own positionalities, with their own backgrounds, and especially if there's a mismatch between who wrote the text and who's interpreting a text, of course, there could be misunderstandings. And something that a colleague of mine at Guesses has looked into, and Leon Fröhling, you can check out his work, is using persona-based prompting. So getting some diversity in by not just telling the LLM you're a survey researcher, but like, imagine you're a 30-year-old highly educated woman who's annotating these tasks, or imagine you're a 20-year-old student with no expertise, to kind of get a bit more diversity of perspectives into how we're coding the data, to kind of try and eliminate biases that just come from our very narrow, and also the LLM's possibly very narrow perspective on understanding. Whether that is something that improves the coding or not also depends kind of like on your, let's say, well, motivation or your understanding for what constitutes bias or not. Like, is diversity good in and of itself? Should we do it for its own sake? Or is it really kind of like we're trying to get closer to the demographics or understanding what the people gave at us? Coming back into, if we're thinking once again about kind of bias of performance for different authors of texts. And then finally, we could look at the intercoder reliability of different LLMs. What if we, instead of asking 2 humans for double coding, we use 2 LLMs for double coding? And then how much do they agree with each other? There's also another colleague at LMU, Jakob Beck, who's looked at that, not specifically in the context of open-ended responses, but in the context of just LLM labeling as well. And that is very interesting and insightful work that I also encourage you to check out if this is something you're interested in. So to take away, results for coding open-ended responses with LLMs depend on the LLM that you use. It depends on the prompting and tuning approach that you use. It depends on how complex your data is, both in terms of topic, in terms of language, in terms of how many categories there are, different levels of complexity, which means there is no one-size-fits-all approach, which means validation, validation, validation before you use anything. And lastly, it means humans still need to remain in the loop. We can't just outsource this. You can find the full paper, the QR code, and the code is there as well for reproducibility. Super happy to connect now in the room or also on the chat, but also you can always email me and ask me about this. Thank you so much.
I have questions. If you join online, you can either unmute yourself or raise your hand and or post your questions in the chat.
I have a question, but it mostly is because I didn't really understand everything. And one thing is that you said you had zero-shot prompting with examples, and it felt like the examples came from the same source as the classification, because that's something I didn't understand quite. Because if you give only one example, you only take 22 away because they are already in the same data set. And that's why I was a bit confused, but now I see it better. That was just too fast. Okay, so and then the other thing that I didn't understand is like with the fine tuning. Before you said that you always randomize the order of the 22 categories, but in the fine tuning it looked like in the code examples. But sorry, maybe it was just too quick. It looked like they were done in the same order by the fine tuning, and that's something that confused me. So did you also for the fine tuning randomly change the order of 22 categories or not?
That's a really good question that they don't actually remember. So I should check. So for the just to clarify or make sure that we're on the same page for the first question. Yes. So so for the fine tuning or like first of all for two-step prompting, right? Because that's the first thing you were actually referring to. Yeah.
No, start with definition. Sorry,
It's two-step prompting. That's fine. There's lots of terms. So exactly. We randomly sampled one example from each category. Actually, no, it wasn't random. I stand corrected. It was an example that we had in our coding scheme because they were like prototypical examples. We wanted to make sure that this is something that's actually super helpful. Yes, and so then those were removed, right? So then the data set was slightly smaller, and then for the fine tuning, we removed this larger part, like 80% that we used for testing, and then 20% for training. And there, actually have to check whether we randomize it. So we always randomize it in the prompt, right? So like when we were actually asking the LLM to classify, when we were fine tuning. So I can't tell you from here because I only have the snippet here. What you see on the right-hand side, though, that's just the introduction, right? So like that'll always stay the same. When it comes to the actual categories in there, I can't actually tell you from just this presentation whether we randomized it in there as well. I want to say yes, because we use the same kind of like randomized prompt, except instead for prompting the model with it, we put it in the fine-tuning data set, but the prompt was the same. So we once like randomized the categories, created a variable with that, and then we just used that for fine-tuning. So imagine the prompt as a variable. So you have one column with just the prompts. And since we had that already, like the randomization was already in there in the text, we could just feed that back for the fine-tuning as well.
Cool, thank you.
I don't know if I'm moderating or you. Okay.
Thank you from my side. Really enjoyed the workshop. Really were some interesting insights. I have two quick questions. First, like just for understanding you on the max tokens you give an API, you give an LLM. Do I understand that correctly? That the LLM itself doesn't know about the max tokens, but it's kind of an environment variable that simply cuts off at a certain point. And is there any way to tell the LLM or to say the LLM, okay, you can use maximum of 80 words and does that work? And I think on one you touched a bit, but I just wanted to ask again whether I think you didn't experiment, like you did kind of one prompt per, or you did kind of one open-ended response per prompt. Yeah. I was wondering because humans would do, like when I think about qualitative coding and also probably how the human codes were done, you probably do 10 or 100 codes, and then based on that you kind of find the categories better, and like whether that would also improve the performance of an LLM. And last, you did kind of with 80% of the examples, you did the training and 20 the prompting. I was wondering, did you try or do you have any experience with turning that around? Because for practical purposes, I ideally would be interested in just having 10 or 20% of training data, because that's the expensive part there in a sense, and whether then the fine-tuning works similarly well or not. Because I think with the setup you could do that with.
So the first question was about the max tokens, and you asked whether so it sounds like the LLM doesn't know that it's going to be cut off. I mean, on a general level, I would even say, like, what does an LLM even know or not know? But like at some point, like we don't know. Some of these processes are super intransparent. So like from, let's say, what it looks like, from what we see, it doesn't know, right? Whether in the back end, like on an engineering like side, there is some sort of information relayed, I can't tell you. Of course, there are ways to kind of like influence this front end by saying, please keep your response short. You shouldn't use more than X words or whatever. Works better now, once again, than a few years ago. I think, for example, if you ever tried this out, if you ever asked an LLM to like write a 500-word abstract for a conference, it didn't write 500 words because it didn't have an awareness of like, or asking it to count the number of R's in the word strawberry. Not prime example. It's gotten better, or they have gotten better. There's no way. So probably that approach would be more successful now, and then we wouldn't run the risk of this kind of like cut off. So classic social science answer, it depends. Second question was about, I know the third one was about the 80-20 split. What was the second?
The second one was whether you tried kind of the one example per prompt or
yes.
one open-ended answer.
That's actually a super fair point, right? Because humans don't code or do anything in isolation. We always learn from past experiences. So I would concede that if we're trying to emulate a human process, it's contrived that we're asking the LLM to not learn from its past experiences. I think there the motivation was more that we would, that since it's a probabilistic process, there might be this tendency to like be repetitive, and also if you're looking at older autoregressive models, it's just like repeat the same sentence over and over and over again. Whereas with humans, we have more insight into the cognitive processes and know that this learning can sort of like ideally be a good one. I think this would be a super interesting conversation with psychologists as well to see like, well, how does past coding performance with you impact like or decisions impact future decisions? That is a very valid point. I think it was kind of like more to avoid this tendency of machines to repeat themselves or like be biased in that regard, because they are trained to be like consistent and since we put the temperature at 0, we kind of like we want to over-engineer that and always assign the majority category. 80-20 versus 20-80. So traditionally, the 80, like a lot of times it's 60-20-20 because there's also a validation step used a lot of times in machine learning, right? We didn't do that here because actually the loss converged very well. We were very happy, so we just, didn't have to hold out data for that. So kind of like based on that, this is just a very traditional split. This doesn't mean just because it's always been done that way, it should always be done that way. But also if we're looking at the amount of data, so at some point it's not even just about the relative share in terms of split, but also like this was a comparatively small data set to train an LLM on. So if this was a larger data set, then probably one could go down. Or at some point you flip it, which goes back to the question I posed at the beginning, like what's the minimax? How can we optimize? I didn't test it simply because it probably wouldn't have been as successful, but it would of course be a nice experiment to see how big the difference is. But also of course this relates to we're thinking if we're getting really into like fine-tuning technicalities like and the number of batches and sets comes up really, really small, and then just the mathematically it gets a bit icky if we have too small numbers. So, but yeah, it would be interesting to check out. Those were that's a great question.
Thank you.
Leah, I did not remember whether we ever came across the point that in the prompt it's written you are a survey or Umfrage-Expertin, so the female form of it. Because in survey research we do see it matters whether the rater is like male or female. Maybe at the open question part with like how did you like the survey, not so much as for other parts. Do you know any research about this, like whether you take the female form or the male form for the LLM, whether this shapes the results somehow?
It's cheaper. Probably should closely read Leon's paper again too, because I don't remember the results, but I'm sure he has insights on that. Yeah, it probably matters. And I will say that this was a microfeminism of mine. But yeah, it would be sad if the male performance with using the male version in German would be better.
Just a question. Would that be another token, the EN at the end of Experte? So would you pay more because you asked it to be an Expertin instead of an Experte?
Could be. I haven't put it into the tokenizer.
I was just
I mean, could be, could not be.
I have sometimes of questions too, and that's something that I just don't understand still. Why was it so hard to force? And not like why was it so not hard? But what do you think? Why were you so unsuccessful in using this other remaining category instead of the NA category? Like where comes this discrepancy? Like if I have like this one category that's like everything that doesn't fit in the other 21 categories, why does the LLM think I can't use that? I have to say none of the previous. I'm just trying to understand that.
It's a good question. I think because or not because, but what I do know is that as humans, like in the other category, we just had this kind of like something, let's say, more substantial that doesn't fit into any of the categories. So it was like, some sort of reason we tried to be like holistic, but like something that's just really not a particular like reason, as opposed to, so there's a difference between writing nothing, like nothing as a word, and writing a dot. Like nothing means like I have no reason for participating. I just did it. I didn't think about it, whatever, versus dot is just like, we actually don't know whether that was I have no reason or whether I'm too lazy to type in something. And I think that, let's say, conceptual distinction isn't as obvious maybe to a machine than it is to us with a lived experience and kind of like lived brain. And like an LLM doesn't know we're not motivated to type in something in a text box, right? That there's a difference between writing nothing and making that effort. And so I think that might be part of the reason, actually. Why tech? I think, did you have a question? No.
Actually, thank you for the great talk. Was data privacy not an issue when sending the open-ended question data to ChatGPT, not running the analysis in an open environment?
We did have those concerns, and that's why we used the Azure Open AI environment. So there, at least, we were on European servers. So it was a concern, and we tried to work around it. We couldn't, at that point, there were none of these like OSS models that you could also host locally that OpenAI now has. But so this was kind of like our middle ground solution for still being able to use a proprietary LLM, but at least keeping it on European servers and not US ones.
Thanks for the presentation, really interesting. I appreciate that bit in the middle where you explained LLMs to us, because it's very much not my field, so that was very useful for my understanding. I'm wondering about this variance between models, for example, in terms of how good it was at getting the same responses both times around. Do we know about the mechanisms why that's happening, why you get this variance across different models? Is it because I guess we don't know about ChatGPT's training data, that's private. So do we have any idea at all about what might be causing this difference?
So you mean now this kind of like running it? the thing twice, and like difference between models when it comes to that. So like whether it's perfect for Mistral and not perfect for GPT, kind of. No, this shouldn't happen. It does. So that's an issue. Yeah. I mean, probably if you talk to some computer scientists or people that are, you know, even more steeped in like building LLMs themselves than I am, even more. I haven't built any, so then probably they can give you some more nuanced answer. But at least I couldn't answer that. Right?
Yes, really, but first of all, thanks for the great talks. This was super inspiring. 3 questions, partly interrelated. The first, why was SVM so good in getting this job done? So that was really one minor detail that surprised me a lot. And then the second, third questions are more from my own perspective as an LLM user, which I've also used for classifying open survey responses. And I would just like to know whether my intuition is correct based on your experience. So 2 things that I've stumbled upon are first, that applying or like providing examples as in one or a few shadowing doesn't help much, but definitions can help a lot, especially when you include both positive and negative definitions of each category, in the sense that you purposefully exclude things that were previously misclassified, so iteratively optimize the prompt in a way. And then this is probably the bigger question. Since you have a fairly complex multi-categorical classification problem, right, with 22 categories, I think you can have it quite easily that the wrong, like the modal category in terms of the probabilities that the model generates underneath the hood is just marginally higher than perhaps the correct category that you get this classification based on choosing the maximum probability category on the map. So I was wondering, have you tried running sequential binary classification tasks to see if, I mean, I understand that these should be mutually exclusive in the end, but they may nonetheless be correlated / conceptually adjacent. So if you run this sequentially and allow for multiple labels from separate classification tasks, would the correct task then be included in the range of true categories?
Thank you for the questions. Again, relating to the first one, why was the SVM so good? I will relay you to my co-author, Carol Hensch, who had like first author on the study that we based this on, and that's actually not something that I was involved in. So we just kind of like used the pre-labeled data from that study. I don't know what magic she did to the SVMs. I haven't been that good. Regarding the second question, we didn't, picking up on the sequential prompting first, we didn't do that. Like that's one of the open questions that I had, like would that be a good alternative to kind of like, yeah, iteratively ask for each category, like you said, binary. Might reduce the complexity. Like I think there's a fair intuition in trying that. And also then if we're thinking of of this as a space, as a numerical like space of like yes and no's basically, or ones and zeros, and then hope that the correct category would be in there. I think that would be that's a good intuition. And then I guess the question that comes after that is again efficiency, because of course, even though the prompts are shorter in terms of we only ever have one category that we're asking it to assign, we have to run that prompt 22 times per thing, and we again every time probably have to say, you're a survey researcher, please do this. So one would probably have to test it and see whether like where the utility curve is, right, in terms of performance and cost. But it's a fair point. Then regarding the description versus giving examples, I've seen conflicting evidence actually. So there was this one, I think, study also in political science that was about classifying political text that said like, oh yes, give the whole code book, give every definition, and like that will help so much. And then for example, yeah, here we saw that it didn't help that much, but maybe the definition, like you say, maybe it's about what kind of definition you give, not just whether you give one. And if that definition, like you say, contains positive and negative examples, that's almost like future prompting, right? It's like it's not as explicit, it's not as like in your face, like just code, but actually really just like this belongs to that, this doesn't belong. So it's more like pretext as opposed to probably, let's say. So I think maybe that's the reason. Maybe this is it's a middle ground, and then that would also be a solution. So I think those are good intuitions and probably worth experimenting on. Yeah.
Question. So first, I was intrigued. You had and you showed some examples for your short text that you dealt with, right? It was one word or 3 words or something. Can you say a bit more? Was kind of the length of the response in some sort more informative or less informative? I mean, was the classification better for longer response than shorter one? And also thinking again about this token principle, are typos and this kind of misspellings, is that an issue in some sense?
So for the first question, we didn't analyze whether there was any connection to kind of like any characteristics of the text, whether that was response length or whatever. Once again, I've recently read a forthcoming study that found, or like there's also other studies that say that there are definite differences when it comes to how long the text is, and also like how many labels are in there. Again, this wasn't relevant here because it was only ever really one, but especially then if it gets more complex, then that might be harder. Again, would be like so many follow-up papers. This would be super interesting to look into that. Your second question related to kind of spelling correction, stuff like that, and typos. Again, we didn't systematically analyze this, but we did find that also, once again, considering I know that like I saw the raw data and there were a bunch of typos in there, we didn't do any pre-processing at all, which is a huge plus compared to like older machine learning models where you have to do that, right? Like you have to spell correct because, but it does appear to me that LLMs are able to kind of like hop over our typos just as humans are. Like they know that if somebody with dyslexia is not too heavy, then probably the right word like should be this one. So I think that might not be as much of a concern. However, again, if this is correlated with maybe other sociodemographic factors that some people tend to write in ways that are less understandable, including spelling correction, misspellings, but also like maybe other like expressions or whatever, that they might actually be worse performance. But I think just that, like given all else equal, I think small typos wouldn't be an issue. One pro. Once that's a good thing.
Also wondering really into this costs and can you say more how sensitive
Yes.
all
This is an appendix slide. Yeah, so this really was kind of only just over 100 euros for everything. So one iteration of fine tuning was €6 for everything. So the tuning, the deploying, and then running it, and then the zero-shot prompting. It's like nothing. You see with the descriptions, because of course the descriptions were the longest. They took more money. And then again for the open models, they were like we got them for free because they include the variant state. But of course, if you have to rent that from somewhere you don't get it for free, then that might be kind of like in the range of like €10 depending on the prompting approach, and then another €15 for the fine tuning. But also depends on kind of like how efficient you design your process in terms of how fast it runs. But so again, this is nothing compared to humans sitting over this for a couple of weeks. But
Finally, I was also wondering now, I mean, you mentioned 1.5 years ago the study was done. Now, thinking of today, what would be your go-to models if you were to redo this? And you mentioned so many more new models came up in the meantime. What a combination of closed versus open models?
I think I would lean towards open models because I think they've gotten better. So, and there have also been these papers out in Nature and Science about they're not like using closed source models for research just requires an explicit justification. And I don't think at this point, like personally, that I would have that justification. We see here like the performance, yes, but also I didn't test the fine-tuning for the open source model. So I feel like, maybe then that would actually lead to a performance that is equally as good as a fine-tuned open source closed source model. And then that would achieve the deal. When it comes to what model family exactly, I honestly can't tell you simply because I haven't actually actively worked with models in a while, and I've been more on the theoretical and evaluation side of things conceptually. But I know that other people in the space are testing, for example, Quen models, which is a newer open source family that has also been shown to be very good. Apparently that's very popular. So that's maybe something to look into. Any more questions about it?
I just have like one question. Why just because it's interesting. Instead of the way you did it, you could have, or maybe you did it and I just didn't mention it here. But I thought you can have like a system prompt and a user prompt. And why didn't you give like much of the background around as a system prompt instead of the way you go? I mean, I understand the argument of the randomization, but I'm just curious, like why you decided to do it like this.
Has to do with another aspect of like us resetting the model after every run. So not even so much about the randomization, but like if you're like clearing the model's memory, you're also clearing the system prompt. So there, it doesn't help you much, but if you put it in the system prompt, and again, like fair point, when it comes to like preparing after a human cognitive process, had we not reset it, and we could have just put it in the system prompt and then just given the response in the user prompt. Totally fair approach. Fair to think about it, but it just didn't make a difference since we were resetting these.
Thank you. For all those interested, I looked it up in the tokenizer and it seems not to make a difference if you are like
Might be different for different models though.
Yeah,
different models tokenize
different.
Yeah, okay. Yeah, no, totally. Just again, we can't generalize ever. Hey.
Well, one last thing, because you said like that you had this like conclusion that the drawn from the short-term reliability, that's not always one, that the long-term is maybe worse. And I'm just like wondering how you came to this conclusion because you didn't show that.
Yeah, I forgot to just, talk about that while showing it. That relates more to kind of like the inherent properties of proprietary LLMs being proprietary, which means at any point in time, if you go to like a GPT platform where you like use those models, they could just say like, no, GPT-4 is retired now because we now have GPT-5, 6, 7, 8, and so we don't even, want to deploy that model. And so then that means, on the one hand, for replicability, that's just bad. We can't replicate old studies. Actually, a few of my earlier papers used like GPT 3.5. You can't replicate that now. Well, on the one hand, and on the other hand, even while they're not deprecated, there might be changes to the model that you have no control over. So for example, if we're thinking about, all of these examples that we've seen about LLMs creating these terribly stereotyped images of people, if you were saying, I don't know, show me a stewardess or something, and also sometimes really like sexist or racist output, then after a lot of backlash, the developers actually went back in and fixed some of the alignment procedures there in the back end on some of the guardrails for that output not to appear. That doesn't mean it's like not in the training data, right? But we just don't get the output. So there's a little filter there, and then the model still was the same, right? Like we could still access chatgpt.com. It just changed on the back end. So even if it's still available, there might have been changes that lead to you not getting the same output, even for something like this that has nothing to do with sexism. So that related to that. Good point. I didn't mention that. Thank you.
Thanks again, Leah, for the great talk. Social Science Data Lab will be a talk by Leon Behrens on May 13th on modeling causal heterogeneity with machine learning. Thanks for joining and hope to see you next time.